Good morning, guys, and welcome for this live session today. We have a few topics I need to cover myself. If you guys have any questions, please do ask too. And let me get through to the ideas first. We have several things this week. We have chapter 5 and 6, and that will put us right in midway, basically where we need to be. There are 2 quizzes this week and also a participation quiz, which is basically the review for the exam that I urge you, all of you, to take. And the rubrics for how that is graded is actually on Canvas too. So please look at that and make sure that you earn your points for doing that. And also the midterm will be posted Saturday around noon, and then will be available until midnight until almost midnight, actually 11 p.m. That's my deadline always for submitting work on Monday. So that's basically how this thing is working. So hopefully, guys, you will take the time to do the quizzes for this week, go through the materials for this week, and also make sure that you are in basically full control of all of the topics that were covered so far. And then take the practice quiz, which should be available from Wednesday until the end of Friday, to make room for the actual midterm to be available on Saturday. So that's the plan, basically in a nutshell, for this week. And starting from next week, we will be actually getting into more basically objects of the solar system and so on and so forth. Svetlana, do you have a question before I start? No? Okay. So let me share with you the ideas that I want to basically go through. So let me share a screen here. And let me get the chat session first going, because I didn't do that. What is it? Okay. So this is the things that we were supposed to cover in chapters 5 and 6. This is chapter 5 actually, and chapter 5 deals with the with light. The reason why light is important is because nobody went to anything outside of basically the moon and some of the inner planets and the some of the outer planets like Jupiter and Saturn and things like that, to actually go and do an analysis of anything. I mean, even the sun, we didn't go to it. I mean, we didn't actually land on it. There is no way we can do that. So the only information we get about the celestial objects in general is through light. So that's why the light is very, very important. We have to have an understanding on how is that. You will hear a lot of the articles, basically, and the things in the news that talk about this specific star, for example, has this much hydrogen in it, or it has this much helium in it, or it's supposed to be of such and such basically part of its life cycle. How do they know that? How would we know, for example, stars that we have never been to, that they have so much hydrogen and so much oxygen, so much hydrogen and helium in them, if we didn't really, if we can't go there? The answer to that is simply has to do with light, basically, okay? The light received from there is a signature of what that star or what that object is made up of. Basically similar analysis done by people who are in forensics, for example. They go and analyze, for example, substances by shining light through them and seeing which light is absorbed and which light is not, which light is transmitted. The light that is absorbed usually is a signature of some elements, specific chemical elements in those substances. That's basically why light is very, very important for us. We have to understand that. Furthermore, light is actually, you will hear them also tell you that such and such star has a temperature of twice the temperature of the sun, for example, or less than that of the sun. Again, this has to do with light. A lot of the information we get about objects in astronomy, they are related to basically spectral analysis. Basically, analyze the spectrum received from those stars. So that's basically what the whole purpose of these 2 chapters are. The first one actually deals with the theory of light, and the second one, chapter 6, deals with the devices, namely telescopes, that are used to collect this light and analyze it, look at it with the naked eye first, try to see it, and that's what the early technologies was, using basically the visual capabilities of humans. But then later on we realized much better chance of doing this analysis using computing devices which have better basically resolution power. They can actually distinguish between far more finite elements, and they can compute things much more quickly than what we can do. And at some point, for example, our eyes are limited only to the visible light. Computer analysis can go below that for frequencies that are a lot less than that in the infrared region, for example, and below. Or they can go for higher frequencies, which is ultraviolet and sometimes the X-ray analysis. So that's basically what this whole 2 chapters are about. So the first chapter, chapter 5, deals with the theory of light. The theory of light evolved, I mean, ever since humans basically started to seeing light, they wanted to understand it. And earlier, we believed that light travels with an infinite speed, basically. It was until the Middle Ages that a sound argument that was made that this cannot be true. Because if light travels with an infinite speed and so many stars out there, then the day and night should be the same. They will all should be lit. But then they are not. I mean, there is a difference between the day and light. The day we have the sun, which is nearby and floods our environment with light. So we have light during daytime. But whereas during nighttime, we have, yes, a lot of stars, but they are far away. And because light takes a finite speed to travel, that's why it's taking so long, basically, to come to us. And the night is as light as the day is. So that's basically the argument that was made. But then attempts at measuring its speed were failed, basically. And actually the first known or documented attempt at measuring its speed was by Galileo. And Galileo, what he did was basically he had a friend basically come, and he told him, okay, I have a lantern in here, and you have a lantern in there, and we go to on this side of the mountain, you go to the other side of the mountain, about a mile away basically from each other. And he's told him, okay, when you see me cover the light of my lantern, cover yours, okay? And of course, Galileo did not have really a clock or a watch to measure the time between these two. Basically, in his thinking is, if I cover it, light will be basically gone for, and it will take so much time to travel that whole mile for him, for his friend, and his friend will react by basically covering his. Now, if he can measure that time, the delay between these two actions, he should be able to find the speed of light. All he has to do is divide a mile by that time, and now he has the speed of light. And like I said, he did not have really a device to measure the time. So what he did, he used his pulse. Okay, he used his pulse and counted how many pulses that lapsed between the two events. Well, he did this several times. He was known for meticulous data collections, and that's one of the things he did very carefully. And he collected a lot of data. Then he called his friend, okay, let's come in here together and sit next to one another, and we'll do the same experiment, basically. I'm here next to me. Do not cover your light lantern or turn it on or whatever that is until you see the light go off. Don't react based on my hand, okay? Because now you see me. So the point being, in here also, he was able to collect the data when they were very close from one another. When he compared the two sets of data, he found that there is no difference between them. So he gave up this experiment, and he thought that this is no good. That basically what he was doing, he was measuring the reaction time, his reaction time and that of his friend. He was not really measuring the speed of light. So that's one of the known experiments, but that failed because the reason is because the distance is very short. I mean, 1 mile is not big enough distance to really see the difference in light. So it's because now we know the speed of light is 300,000 kilometers per second. That's, you need about 300,000 kilometers or what, about 200,000 miles to really see 1 second and the delay. And since he was using actually a very lousy also watch that did not really detect the finite changes in time, so that was also the reason why this whole experiment failed. It was actually the first known way of measuring the speed of light was due to Romer. Romer basically in the toward the end of the 17th century, basically, there was the hypothesis of Cassini that basically the reason why there was a delay, because we have discovered Io by that time. Io is one of the moons of Jupiter. Io takes about 42.5 hours to go once around Jupiter. And because Jupiter is further away from the sun than Earth is, so it takes 12 years for Earth, for Jupiter to go once around the sun. So Io, meanwhile, is taking 42 hours and a half to go once around Jupiter. So if we look at it now, for example, Jupiter and the Earth, let's say, for example, that they're lined up this way, 6 months from now, the Earth will be on the other side of the sun, whereas Jupiter and Io with it would have barely moved in their orbit. Because of this spin of Io around basically Jupiter, there was a delay in the light it takes to come to the Earth 6 months from now, basically. And that delay is due to the light taking extra time to reach us when we're out on the other side of the sun, because of this, which is, we know today that the distance between the Earth and the sun is 150 million kilometers times 2, because we are on the opposite side. So you're looking at 300 million kilometers. Well, light takes a lot of time to reach that speed. It takes about 16 minutes to go that extra time. So there was a delay. There was a difference in the 42.5 hours for the Io moon to go around the Jupiter. And that's how Romer actually was able to estimate the speed of light to be about 200,000 kilometers per second. It was off, but that was really the first number to be put for the speed of light. Of course, later on, the experiments there were better experiments using gears, basically, by Fizeau, and Fizeau was able to give us better estimates for the speed of light. So we know now the speed of light is 300,000 kilometers per second. That was one thing. Also, light exhibited some known, for example, when light hits a surface, it bounces off so that the angle of incidence is equal to the angle of reflection. That was one thing that was known. Light also can be transmitted from one medium to the other. Think of the surface of the water, for example. The surface of the water, you can see under the water. Why? Because light hits the surface of the water and goes and hits the bottom of the surface of the lake and comes back up. We can see the fish, for example, under the water. But light doesn't really go straight out between the surface. It breaks a little bit. It goes at an angle. That's called refraction. So the laws of reflection and refraction, they were known at that time. And there was kind of a difference between, was light particles hitting the surface or is light wave? Because later on, Mr. Young in the early 1900s, in the early 1800s, he did experiments and he found that the light exhibited interference. So light is a wave. It has a wavelength. He was able to measure the wavelength, actually. By the end of the 19th century, around 1870, Mr. Maxwell came up with a theory that explains everything. That light actually is a wave. He was able to find its wavelength. He was able to find its frequency. And he was able to match its speed with what was actually known for light. Not only that, but he went beyond light. He went to, he found frequencies that our eyes are not sensitive to. High frequencies like, for example, ultraviolet light, X-ray, gamma rays, and low frequency light, for example, that our eyes cannot see. They see them black, the color as far as we're concerned. And that is also the infrared, the radio waves, and basically the very long wavelengths so that we can see. So that's basically the microwave region. All of these things are actually for low energy, long wavelength lights. So that's the whole theory in a nutshell, and how Mr. Maxwell arrived to this one. Then also we can measure the intensity of the light, basically. So the main characteristics of light, and this is very important when we're talking about light, are, let me get this marker in here, I'm sorry. They are wavelength and frequency, okay? The speed of light is for all of them. So if you have a blue light, for example, and a red light, the difference between them is their wavelength and frequency on one side versus the wavelength and the frequency of the other one. Light travels with the same speed in the same medium. So in vacuum, for example, or in the air, it travels with 300,000 or 300,000 kilometers or 300 million meters per second. That's the speed of light, 3 times 10 to the power 8 meters per second. So that's the same speed in vacuum that is provided, because in water, for example, it travels a little slower than that, and that is what is known as the index. That's what causes actually light to refract. Okay. Questions so far about this chapter, part of the chapter? No? You have an example in here. I don't think that I talked about in the notes that I have for you guys to summarize things, and that is the intensity of light drops like 1 over distance squared. Okay, so because light is emitted by the light source, and when it travels through an entire sphere. So whatever it was initially near the surface of the light source now has spread throughout an entire sphere. And the area of the sphere is 4 pi times the radius squared. 4 pi times the distance squared, basically from the origin to where we are right now. So that intensity now drops like 1 over distance squared. So the question in here is that you have a 120 watt light bulb. That's the light bulb that you go to Walmart, for example, and grab. That's a very bright light bulb, 120 watts. You take from there at a distance 2 meters. It says in here in this example is 2.4 watts per meter squared. So this is meter squared, not M2. Okay. What would be the intensity of light if the distance is doubled? So basically, we were at 2 meters. Now we are at 4 meters away from it. 4 meters is basically, we doubled the distance in this case. Since it drops like 1 over distance squared, it was 2.4 to begin with, watts per meter squared. Now it's going to be 2.4 divided by twice squared. So it's going to be 2 squared. So the answer, of course, is going to be 2.4 divided by 2 squared. And the answer should be, I'm pulling my calculator quickly in here, 2.4 divided by 4. The reason why I'm dividing it by 4 is because the 2 squared in here is 4. So the intensity drops to 0.6 watts per meter squared. So that's basically how much the drop is in terms of the power of that light bulb. So if you're very close, I think this is intuitively basically what we see. I mean, if you have a light bulb and you're near it, it's bright. When you're moving away from it, it dims. If you move further and further and further, the light bulb will become dimmer and dimmer and dimmer. At some point, it will not be visible. If you're 10 miles away, for example, even at 120 watts, you're barely going to see probably a dot in the sky because the intensity drops like 1 over distance squared. This is intuitively. If you want to have better, basically, lighting, you have to bring the light bulb closer to you. So if you're reading a book, for example, at night and it's pitch dark, then you have to be close to a light source. In this case, for example, the light bulb. So that's basically what this idea is in here. And the same thing with the stars. 2 stars that have the same power, basically, they emit the same power. One of them will appear dimmer than the other because it's further away from the other one. The closer one will always appear brighter. So that's basically what the idea behind it in here. Provided they have the same power, that they're emitting the same power. Now, if the further away is far more powerful, they may appear at the same intensity because the further away will compensate for its distance by emitting more power. So that's basically the idea behind it. The same thing with the light bulbs. For example, if you bring a 40-watt light bulb and a 120-watt light bulb, even though probably the 40-watt might be closer to you a little bit, but it's still probably the 120 will overwhelm it because it has more power. Provided the power is the same, the distance matters. If the distance is the same, then the how much output is going to matter too. So that's really how the idea about it. But the output is really linear. The distance is square. The further you go, the faster it's going to drop with the distance. So that's basically what this example is about. Then So hopefully that you guys are doing the exams. I know I put them in there also as notes, and you guys are doing them. They're powerful, and they can teach you things in here that you learn from them, basically how to manipulate these numbers and what they mean. Because if you just read through the chapter without actually doing the examples, the things, first of all, do not stick. You're not going to remember them at the end of the day. So I urge you guys that you do all of the examples that are mentioned, including the ones that I don't really take note of it. The ones that I take note of it because I believe they're very important to help you understand more on how astronomy works. And when people talk about stars, for example, this star is a classification, that star is classification, this star is a main sequence star, and it has this much, for example, classification, that is its actual surface temperature. Which brings me to the next point in here, is that if we look at stars, and we see this star is yellow, and this star is white, or this star is blue, what we're looking at is basically where the maximum of the wavelength is, where the maximum of the power is coming from. The power given star with the wavelength, the intensity follows this curve. And then I posted this curve, and this curve drops with the temperature. The maximum in here drops with the temperature. So the maximum, the lambda max in here is the maximum wavelength is inversely proportional to the temperature. So that means if I see that there is a yellow star versus a blue star, the blue star in here has a higher temperature because the blue is a shorter wavelength than the yellow. So if I look at stars and I see this star is super blue, that means it has higher temperature than this star, for example, which is a red, for example, or orange, or whatever color that is less intense. The blue is the ultraviolet is the highest. Violet, I'm sorry, is the highest thing that we can see. Then the blue, then the green, then the spectrum basically goes through. This one, we'll talk about the spectrum down the road here. So the point being, this is basically how we distinguish the stars. For example, Betelgeuse, which is a red giant, and also Rigel, which is a super big star, they're different colors, and both of them belong to the Orion constellation. One of them is hotter than the other one, Rigel is, okay? Although in this case, Betelgeuse emits far more power because actually it's a super giant, it's a huge one, but its surface temperature is a lot cooler than that of Rigel. So that's one thing that we can distinguish stars from. And the example in here, they give an example that this is a star that emits 1200 nanometer. By the way, we can see with our own eyes anything around 500 nanometers to about 700 nanometers. So star 1200 nanometers, as far as we're concerned, we can see it with our own eyes. 1200 nanometer star is not a star that we can see because it's a very, very long wavelength. That means its temperature is very short. It has very less temperature. So if I want to find its temperature in this case, well, I use this formula in here, which is Wiesen's law, displacement law of Wiens. So in this case, it's 3 million times, 3 million, that is what this number is, divided by the wavelength, which is 1200 nanometers. The units in here, the temperature is going to be in kelvins, and the wavelength is in nanometer. So again, if I got my calculator, so I'm going to do 3 million, which is 3 times 10 to the power 6, 3 times 10 to the power 6, and divide that by 1200 nanometers. The temperature, it tells me, is 2500 Kelvin. 2500 Kelvin, I mean, it sounds a lot, and it is, but it is not as hot as the sun is. So this is not a big temperature, again, because it's a very, very low dwarf in this case. So it's very, very dim star, okay? Compare that to the sun. The sun looks yellowish, and the yellow is around 549 nanometers. So if I want to use the same formula to find, for example, the temperature of the sun, the surface of the sun, how high the temperature is, I use the same formula, and I find that 3 million again divided by 540, and if I put the numbers in here, 3 million, and you divide that by 540, the answer is 5,555.55, whatever. So it's basically 5,500 basically Kelvin. If you look and consult the books, you will find that the temperature is not far from this number. It's 5,445 or something like that. So that's basically a rough estimate in here because I estimated the maximum wavelength based on my visual eyes. But if I do a spectral analysis, I see that actually the temperature of the surface of the temperature is not exactly 540. It's shifted probably to 545 or 543 or something like that. So that's again my estimate because I know how that's where yellow lives. So that's basically what the star, the sun is. So again, just by looking at the spectral analysis, by knowing exactly the surface, it's just finding the maximum wavelength. If I check the wavelength, for example, for Rigel, I see that it's peaked around the blue color, for example, then I know its temperature is much, much hotter than even the sun is. So that's basically how we can do these things. It's very, very powerful stuff. Then there is the second Boltzmann law, which is, it gives me how much output of power is. So this number is actually in watts per meter squared. How much output is for that star. Again, the hotter the temperature of the surface, the more output of energy is. That's basically a bottom line. And that is actually what you do, actually. If you have an iron, for example, piece of iron, and you put it on fire, please do not use it, do it at home unless you're really properly shielding yourself from the hot surface. You will see that the color of the iron, for example, starts to change, and it's going to start red, and then it's going to shift in color until it becomes white. At that point, it's emitting all kinds of frequencies. It's super hot. And that's before the melting point, because at some point, even iron will melt in high temperatures, and you will not have it anymore. So the bottom line is that it's going to start from the infrared and gets hotter and hotter and hotter, and then emits radiation at that point, and how much output of energy depends on how hot it is. And actually, it's a fourth power law. It's T to the power 4. Man, it's far greater than if you have, for example, the difference between, let's say, for example, 5,500 Kelvin to just 11,000 Kelvin, which is just double basically this number. The output, the power output is 4 times, 16 times more power between these two stars. That's why hotter and hotter stars, like for example, if you look at Ceres, which is one of the stars that is actually we can see in the sky also, it's actually part of a binary. One of the stars is actually a dwarf star that is very, very hot in there. Temperatures can be 25,000 Kelvin or more. So these are super emitting a lot of energy, basically stars. So that's some of the things. Betelgeuse, for example, which has a lower temperature than the sun and emits less energy, but it's spread over a bigger area. So at the end of the day, it's going to emit far more power too. So that's because, again, you have to multiply this number by the area to get how much actual output is in watts. So the bigger the surface, the more power you're going to have, albeit it's probably emitting little by little per meter squared, but it's emitting a lot because it has more meter squared to go to do the thing. So that's basically, in a nutshell, some of the basic ideas that are needed for us to understand astronomy. This is for emitting objects that emit light, basically. So this is very, very important to understanding the stars. Then in here, we're going to talk about the spectrum. Again, I just mentioned it. When Maxwell basically came up with a solution, the spectrum is divided in a very narrow region that we can see between the 400 and the 700 nanometers. This is basically the visible light. Anything longer than the 400 meters, that is going to be the infrared, followed by the microwave region, followed by the radio region. Those are long wavelength. And on the other side, you have the UV, ultraviolet, and then followed by far more energetic and damaging radiation, which is X-rays, and then followed by that, after that, even far more killers, they're the so-called gamma rays. These are bandwidth. These are not specific frequencies. I mean, the visible region, that's what our eyes are sensitive to, they span a whole spectrum in there by themselves. So the X-ray also, which is actually a big region, also spans a whole spectrum in there. So that's basically, in a nutshell, what these things are. Some of the most powerful and most eventful events in the universe really involve gamma rays, which are deadly. And X-rays also ultraviolet by themselves. I mean, if you expose yourself too much to ultra UV, it's damaging to life in any form. And that's why some of the surfaces, for example, of some of the planets that don't have protections from UVs, they can be, we know that at least a carbon-based life that we know it will not be able to survive in those environments. Case in point, for example, Mars. It doesn't have a thick atmosphere to protect from the UVs, let alone the X-ray and gamma rays. So Mars, at least on its surface, it cannot have a carbon-based life form the way that we know it. At least that's what we know. I mean, there are other problems with Mars. This is the least of one, probably at least one of them. This is provided you have enough air, or at least you have some sort of air and liquid and all of the other forms for this life form to exist. Even with that, you still have radiation that is going to be deadly. In a few minutes, basically, everything will be decimated in terms of life form. So anything in this region is very high energy, and you don't want to be near it. That's why when you go for an X-ray in the hospital or in the technician, the first thing he does is he get out of there and he lets you expose for a few seconds or fractions of seconds, at least that portion of your bone, to the X-ray radiation, so that they can do a picture to see exactly where the damage is in the bone and things like that. So these are some of the things that are involved in that. Then this chapter diverts into trying to understand the fact that this is actually Maxwell's version of light. There was in the same time other experiments later on that led to quantum mechanics, that light actually is made out of particles, and those particles are called photons of energy. That's what led Mr. Einstein to actually explain the photoelectric effect using that concept. And that in itself also is so light itself, is it a particle or a wave? That is until today is a debate thing. It's actually both. That's the answer that physics will give you. Light is a wave and a particle in the same time, and this is the so-called duality or nature of light. So this is some of the things. Now, the energy of light is directly proportional to the frequency. These are high frequencies, and this region is low frequency. High frequency, low frequency. High frequency means high energy. That's why all of these things, X-ray, gamma rays, and UVs, they have more energy in them. They could cause more damage. They could kill cancer, at least, if not destroy the entire, basically, cellular structure of living organisms. And they could do more damage, and very hard to detect them, especially for the gamma rays, for example, because if you want to build a detector for them, it's very hard that detector, for example, will be able to even survive them, let alone give you that they have these things in here. So it's a big technical challenge to try to find to at least detect the gamma rays and even the X-rays themselves. For low frequencies, that's radio telecommunication. Any one of you who owns a cell phone or has a remote control or does something, that is actually radio waves and microwaves and infrared. With the remote control, that's actually an infrared and things like that. So those are some of the things that are involved in that. And the key thing in here is frequency and energy they're the same thing, basically, because this H between them is just a number. 6.626 times 10 to the negative 34, that's Planck's constant, okay? So that's really how this thing is. And trying to understand then the spectral lines then from we know, at least some of you have probably taken chemistry, that the atom is made up of a nucleus and an outer shell of electrons, and electrons can only exist in certain energy levels. Now, when the atom is excited, that means the electrons, they are not in their ground state, they're actually at a higher energy levels. When the atom is not excited anymore, they want to go back to their energy levels. In doing so, they will emit light, they will emit specific frequency, and that frequency is proportional to the gap in the energy, to E itself. So between this energy level and that energy level, there is a gap. And each transition would correspond to a specific frequency and specific color that we're going to see. Now, if it was excited, if it was not excited, and you shine on it light, the atoms will move from their lower energy levels to a higher energy levels. And in doing so, they absorb just the specific frequency that corresponds to the gap in the energy only. And that is why we have two kinds of spectral analysis. One of them involves only absorption. It's called an absorption spectrum, where you shine light on atoms, and then they absorb that light, and you see from the other what is missing. Then you'll know what was absorbed. So this is an absorption spectrum. Or you excite the atom by hitting it, or raising its temperature or something like that, and then see what light is emitted from it. So this is called an emission spectrum. So in this case, there will be presence of spectrum, presence of specific frequencies. So that's the emission versus the absorption spectrum. So that's the difference between the two of them. So if I'm looking at a star, for example, far away, that is an emission spectrum, because then I will see the frequencies that are present. Oh, I see the signature of hydrogen. Then I can affirm that there is hydrogen in there. Or I see, for example, light going from a star, that I know its specific colors, that I know its spectrum, but then it goes through a gas, for example, in the interstellar gas, and then I see missing frequencies. Oh, I know then that gas is made up of specific elements that absorb those frequencies. So that's basically the difference between the two. So again, to go back to my initial example of the forensics, they excite the element, and then they see what frequencies are emitted, or they shine light on it, and then they see what frequencies have been observed, and they can say the person had arsenic, for example, in their food or something like that, and they go and prosecute the person who served the food or whatever that is. You see, that's basically the idea between the two types of spectral analysis. Of course, there is another spectrum that we always talk about, and that is a continuous spectrum, and that is unaltered, unaffected spectrum. Spectrum coming straight out. As it came in, it continued to go through, so that's a continuous spectrum. So you have an absorption spectrum, an emission spectrum, and the difference between them is that when it's emitted, the other one is absorbed. So that's the two of them. And again, they correspond to specific jumps in the electronic structure of the atoms. So from a higher frequency to a lower frequency, the gap is small. So the frequency I expect in this case will be a low frequency, long wavelengths on this side. But if the jump is very big, then there's a big gap in the energy. There is higher frequency. Then in this case, there is a short wavelength. Because, by the way, I didn't know if I mentioned that or not when we were talking about this expression here between these two. The speed of light is the result of the wavelength times the frequency. So all you need is just one number in here. So if I know the wavelength, I know the frequency, all I have to do is use this formula in here. This is called the dispersion law. So if I know the dispersion law, then that means that high frequency is short wavelength. And low frequency, which is on the other side of the spectrum, is long wavelength. That's why the radio waves, they're in the meters, sometimes centimeters, sometimes. That's why, for example, in the microwave, when you put food, it's actually in a few centimeters, and that's what the agitation of the water molecules is, and that's what helps to cook the food to be cooked, because the water molecule starts to move around, increasing their kinetic energy, and now the temperature rises, and all of a sudden the food is cooked. So that's the microwave region that we use actually in our households. So these are some of the ideas there. Now, in addition to that, and it's very critical to understand the Doppler effect. The Doppler effect, you guys have had an experience with it, I am sure. If you're sitting in a car or sitting in a train station, for example, you hear the train coming, you will know it's coming without having to see it, just by distinguishing that high increasing pitch of the sound. Now, if the train is receding from you, is moving away from you, you will also tell, without even seeing the train, that it's going away, just by listening to the sound. And you will see that the pitch in this case is actually going toward lower and lower frequencies, longer and longer wavelength. So that's basically how you can tell. I mean, you have three things going on in this case. You have an observer, which is you. You have a source, which is a train or a police car or an ambulance, sirening its frequency. And in this case, the sound has a speed itself. So if you are moving away and the source is, let's say you're stationary and the source is coming to you. So the source sends a wavelength, let's say sound in this case, or light, and then follows it and sends another one. So for you, instead of coming, the wavelengths are coming spaced with their normal space, they're compressed. They appear shorter wavelength, which means higher frequency. But if it's moving away from you, it sends a wave front and moves and sends another one. So instead of them properly spaced, they appear spaced more. So in this case, they appear to have longer wavelength. Okay. So in this case, since they are longer wavelength, they appear to have lower frequency. So again, shorter wavelength because they are compressed. In this case, appear to have higher frequency. Spread, more spread, longer wavelengths, so they will appear to have lower frequency. That's the same thing with light. And that is critical because that was actually the one that helped us understand that the universe is expanding. By looking at specific stars, Halley in the 1930s, basically, Hubble, I'm sorry, what am I talking about? He was able to see those Cepheid stars, basically, that's what they're called. They have specific frequencies that we know of, okay? But those galaxies that have these stars that we know their frequencies are not where they should be. They're shifted toward lower frequencies. That means these galaxies are moving away from us. That means, and then he saw that actually all of these galaxies, they're moving away from us. And that's what he concluded, that the universe is actually expanding just by looking at this kind of stars. Because every single galaxy out there, and the further it is, the faster it's moving away from us, because the frequencies from those stars that are in those galaxies are not staying where they should be. They're not shifted toward the blue color, they're shifted toward the red color. That is why it's called the red shift. That's why the universe is expanding. And that's exactly what you can do today. For example, if you go and wait somewhere and listen to the siren, for example, from an ambulance without even seeing it, even if you have your eyes closed, you can tell, is the ambulance coming toward me or is it moving away from me? That's the same idea behind it, because you have an expectation and you know what the siren of an ambulance needs to be, but you're hearing it either at a lower pitch. In this case, it's moving away from you. That means it's moving further and further away from you. The wavelengths are longer and longer, or it's moving toward higher and higher pitch. In this case, it's coming closer and closer to you. So that's basically, and actually, if it passes you, you will see the difference. So it's moving towards you, even if you have your eyes closed, even if you are sleeping. I mean, not completely sleeping, because you have to hear the sound at least. Even if you, so you can tell, now it's moving away. Now I can go back and continue my sleep or continue my game or whatever I was doing earlier. So that's basically what this Doppler effect is. And it's actually critical also sometimes to measure, for example, things that are moving super fast, especially in the case of a binary, for example, stars. Stars that are in a binary system, the one that is moving towards us, its frequency is shifted toward high frequency, and the one that is moving away from us is shifted toward lower frequencies. So that's basically the idea behind it. So all of these things. So for example, if I expect the hydrogen lines to be in this lines, but then I go and I actually study this hydrogen and I see that they are actually, for example, let me get another color. This is where they are. All of these lines have moved toward this side. And let's say, for example, this side is frequency. Then in this case, I know the star is coming toward me, okay? If they moved toward the other frequency, then I know that it's moving away from me. So that's basically in a nutshell what this idea is. And hopefully you guys have an understanding of what this is. And that's the power of everything that we have in here. Chapter 5 is fascinating. So I really want you guys to have an understanding of it, because it's the basis with which we actually investigate the entire solar system, the entire universe, and everything else. We use light, actually. Light is a very powerful thing in here to study objects in the Now, which brings me to the topic of chapter 6, which are really applications. Now, we're putting all of these ideas together to build telescopes, okay? Telescopes, the ancients used some of the stones, basically hedge stones, for example, to collect light at specific angles and know exactly the calendar and things like that. But actually, modern day telescopes, they are actually, now we have two kinds of telescopes. There is again, I talked about the law of reflection earlier and the law of refraction. There are two kinds of telescopes. There is a reflective telescope and there is a refractive telescope. The one that Mr. Galileo used initially to look at the Jupiter, for example, was actually a refractive telescope. These are the telescopes that are long, and in the bottom you look at them and you see the light coming through a lens and focus toward the eyepiece, which is at the other end of the telescope. A refractive telescope is a different mechanism. So light goes through the telescope to a primary mirror, and the primary mirror, so it's not a lens, it's a mirror, focuses the light on another mirror, which is called the secondary mirror, which takes the light and puts it to the eyepiece so that the person look at it. So one of them uses the law of refraction, and the other one uses the law of refraction. And I know I probably told you guys that you can go onto the AWB website, Astronomers Without Borders, and you should be able to get a telescope, which is, I have it in here. Actually, let me grab it. Okay, here is the one from the AWB website. This is called the One Telescope. It's $200. In the old days, when my students asked me about which telescope to buy, it was always a puzzle trying to explain things and do things like that. But then I think this is it's no context anymore. So just if you really want, if you never had a telescope before, this is the perfect one. I used to have an 8-inch one, but I really hated it because it was very, very hard to set up, very hard to move. So I like this one because actually it's very light, and it can actually do a lot of the things that you need to do. Okay, one of the biggest things in here in this chapter is the area. Okay. So what matters really, so I'm going to stop sharing a screen in here so that I can go back into the view in here by itself. So this is what I mean by the area. So I'm going to take the cover off, if I can find it, okay? In the bottom in there, that's really the area that we're talking about. This is a 5-inch telescope, which is a 130 millimeter telescope. This is not the biggest telescope that you're going to get out there. You're not going to do a lot of things with it, but at least you can see the moon. You can see Jupiter. The other day on Saturday, we saw Jupiter moons, actually, all 4 of them. And actually, you can see Saturn. I don't have a Barlow for this telescope. I used to have 2 or 3 of them. I couldn't locate them. That can double the magnification or triple it. I have actually a 3x Barlow, which is really increasing the size of the image, in which case you will see far more. We saw actually the rings of Saturn with this very telescope, and we saw the moon of Saturn, Titan, so with this very telescope. So this is really actually a very, very powerful one. So again, this is a collapsible telescope. I mean, let me remove, this is actually, this is a collapsible telescope. So we're going to get to this one. Actually, this is a very nice one. So this is how it extends now. And this is how it looks like. So that's basically a very, very nice telescope. I mean, it's very portable. You can throw it in any car you have or anything in there, and you're going to use it for whatever purpose you need. Okay, this is actually an added feature that is, this is a viewfinder called. Basically, it has when you turn on the light on here, you have the infrared light that you can shine on the object. For example, if you're looking at the moon or Saturn or whatever object you have. And then based on that, you're going to use this thing in here. When you put the eyepiece, every telescope needs an eyepiece. This is where you're going to put your eyes in. So you're going to put the eyepiece in here, and you start basically adjusting based on the viewfinder. Once you have the object, you're going to adjust and fine tune. This is one of the lousy things about this telescope is the focusing in here. You have to turn this wheel in here left and right. And if you're not careful, this thing will come off. So you have to put it back and work with it. And again, the primary mirror is what you see in there. This is the secondary mirror that I was talking about earlier. And this is where the viewfinder is. This is a reflective telescope. This is not refractive. This is not what this is called Newtonian telescope, because Mr. Newton modified the telescope that Mr. Galileo used and basically use the law of reflection instead of the law of refraction. So this is something that you guys can have. I mean, the mount also sometimes is critical also to have the proper mount. Again, for this telescope, this is called Dobsonian mount. It spins in here to give you basically the azimuth in this case, the position and the side of the object. And it also when you loosen this thing in here, it's going to give you the altitude of the object that you're looking at, and you can position it for whatever thing that you have in there. So this is when we have class in session. I usually have a lab experiment for my students, actually, where they identify telescopes and determine their powers and things like that. And the power has to do with the eyepiece, actually, because one of the formulas that I have in there, so it depends on this guy in here. This is a 10x, which is really not a great powerful lens. But compared to the 25 millimeter, this is actually a very good one for all purposes. And again, with the Barlow, it's going to be perfect. One of the things that I discovered over the years is that everybody wants to take pictures. So in order to take a good picture with a cell phone, actually, is I got this thing in here. This is not an expensive thing in here. And there was another lab also that I used to do with my astronomy students where I required them to attend the lunar observation. We go and actually observe the moon and whatever is visible on that night in terms of planets. If Mars is, so is Mars. This time of the year, we can't see Mars. Mars is below the horizon. I mean, it comes up, but it comes up around midnight or something. But we can see for sure early on, just after sunset, you can see visibly both Jupiter and Saturn. So we do that. And you take pictures and you share your pictures as part of your lab report and you explain what you have seen, done and things like that. So again, this is to put your cell phone in here and make sure so you put your cell phone in here and make sure the camera of the cell phone and the lens itself, they line up, and then you mount them and you take pictures. After you zoom, after you have your object really as sharp as it can be, then you take as much pictures as you like. Again, this is some of the techniques that I want to share with you guys. This is actually an amateur astronomy, basically telescope that you're very much encouraged, because typically my students, about half of them by the end of the semester, they're interested at least in acquiring their telescope. And because of the budget situation, I think this is a perfect tool. This is something that is very nice, okay? So I thought I should share that with you guys, albeit we're doing an online class. In the case of in class, we do far more with telescopes in terms of hands-on stuff, where you guys actually take the telescope and work with it. The telescopes that they belong to, of course, to the school, and actually go and in the evening, and we do actual observations and things like that. Short of doing that, I encourage you to get your hands as much as possible on one of them and see if you can work with them and at least have a feel for how they look and play with them. And for that purpose, if you have never had a telescope before, I mean, a $200 telescope is not a bad investment, because it's going to be mobile and help you get started. And then if you are interested more, you can get more telescopes. Again, in this example, I have a 1 meter. Okay, what happened to my pen? I don't know where my pen is anyway, so I'll try to use this one. So I have a 1 meter telescope and a 4 meter telescope. This is not a 1 meter, this is a 5-inch, okay, telescope, okay? This is not a professional telescope. But the difference between them, of course, because how much light is collected on the primary mirror is really what matters, okay? So let me stop sharing this screen in here. Before I do that, let me get my stellarium going, because I will show you how to use the, by the way, next week we'll have a lab experiment with the stellarium. So that's why I urge you guys to download it. So let me work with stellarium and show you how you use the telescope feature on the stellarium. So right now we are in, it says I'm in Loma Linda. So let me go into the daytime and change. Okay, let me stop sharing that screen first and share with you my stellarium. So again, we are at 8:54 in the morning. So we're gonna change the time to sometime, let me manually enter it. Let's make it 9 p.m., which is 2100 hours, because again, I told you guys a long time ago that this is, so if I am here tonight in Loma Linda, and actually Riverside is the same thing, and I'm looking at the sky, the night sky, the southeast, this is where Jupiter is, and this is where Saturn is, okay? So I'm gonna go in here to Jupiter, and I'm going to use a telescope in here to look at it. Okay, so I'm going to choose a telescope. This telescope is a 10 millimeter telescope. This is not 10. This is a 10 millimeter telescope. I'm sorry. This is the ocular. This is basically your eyepiece. Okay, it's a 10 millimeter, but this is 125 125 millimeter telescope. This one is 130. Actually, the image on this one will be slightly better than this one, the one that I'm looking at with this one. But the big difference in here, the Barlow. I don't have a Barlow right now, so I'm going to bring that back to 0. Okay, so this is how Jupiter would look like tonight if I'm looking at it in the sky. Let me center Jupiter. This is how Jupiter would look like now. I have the 3 moons only. Europa and Io is behind Europa. You can't see it now. So if I look at it tonight, around this time, which is 21:55, and wait around almost 10 p.m. at that time, this is how Jupiter would look like with this telescope, more or less, okay? I will see the 3 moons. Like I said, last Friday, we saw last Saturday, we saw actually 4 moons, all 4 of them. But again, if I wait a few hours later, I'm going to see Io again appear, because I told you guys Io takes about 42.5 hours to go around the moon. Again, this is a 10 millimeter with a 125 millimeter telescope, and also with no Barlow. Now, if I have a Barlow, look at the image in here, how it's going to improve. This is far more details with this very same telescope in here that we have in use. Of course, you're zooming in, so you have less object in here. I will see. Let me remove the names in here if I can. Okay. This is how it looks like. Okay. What you're seeing in here is it's actually a small moon in here for Jupiter. Okay. So that's basically how it's going to look like with a 3x Barlow. So again, these are some of the features of the software that you guys have in there. So if you don't have a telescope, you have Stellarium, which is more or less realistic in terms of the views of what you see in there. Let me finish quickly the topics that we're talking about. Again, let me share with you the screen in here. Okay, let me finish these topics again quickly here. Again, the chapter 6 talks about the some of the telescopes that are used actually in the today, and you really have to know some of them, because when you're reading articles and you're talking about this telescope and that telescope, you have to have at least an idea of what they are. Telescopes, the biggest difference between them are they in the visible region, because when we looked at the spectrum earlier, not all of the radiation from the sun goes through the atmosphere and comes down to us on Earth. There are certain frequencies that are going to be absorbed by the atmosphere. And that's why a space telescope will work better, because then it will collect all of the spectra, all the lights. If we are earthbound, we're limited. We have the visible light, and we have the radio wave light, and we have only some of the things. That's why on Earth, and even if you have, for example, looking at an infrared is heat really, so those frequencies will be shifted and they don't work well. So an earthbound telescope in here is limited by many factors, by the temperature in the atmosphere, by the moisture in the atmosphere, by the altitude in here. The higher you are, the better it's going to be, because it's going to be closer to basically less of the radiation is absorbed. So that's why there is the visible light telescopes, and they have instruments in there listed in the chapter. Hopefully you guys go through them. Radio telescopes, and actually it's a very, very powerful technique too, that enables us to understand far away object and how they interact. And sometimes there is a so-called short burst radio signals that initially we thought that they were aliens actually transmitting to us, and then it turns out to be just no more than binary stars and things, actually neutron stars emitting those frequencies when they spin around their axis at so high frequency in here all the time. And then we have observations outside, and that is the Hubble telescope and the Kepler and all of the, I'm sorry, Kepler was specific just for the studying outside of the outer planets. I'm sorry, exostellar solar exoplanets, planets that are outside of the solar system. And then the future telescopes, and the biggest one that is coming in 2021 is James Webb Space Telescope, and that is going to at least replace the Hubble, and it's supposed to have far more power, and hopefully it's going to teach us a lot. The Hubble already did so much for us, and hopefully you guys go through the notes in the chapter and answer the questions in the quiz and things like that, and things that are in a nutshell what's going on in this chapter. Any questions so far? Rachel? No? Okay, let me summarize these things. I know I talked a lot. You have 2 quizzes this chapter, this week, because of the 2 chapters. And you have the review quiz, which is coming starting from Wednesday, I believe, until Friday. Hopefully you guys do it because it's graded. And then you have the actual midterm that starts sometime on Saturday and ends on Wednesday. There should be nothing due other than the midterm in that span of time. That's basically in a nutshell what's going on. This recording will be basically as taped, and it's going to go online, hopefully to help anybody who did not attend, because again, attendance is not required because this is an online course. But again, I saw that a lot of people actually go and watch these videos more than the ones from the lecture. So I'm going to be using more and more of this to help you guys at least follow the note while you're reading stuff and have hopefully some of your questions answered. And you're welcome to ask any question again on Canvas. Hopefully you ask them in the discussion boards, and some of the discussion boards in the future will be graded. So that's where you ask or make your comments for these chapters. Any questions, guys? If you don't have any questions, I'm very, very happy that you guys came in. Please do attend. I'm grateful for that. Attend the lecture because it only makes the topic richer. Ask questions to enrich it, and your classmates and yourself will be thankful for doing that. Thank you, and be safe, okay?